Hi everyone, and thanks for joining us again. We're going to take a look at matrix multiplication. Can any two matrices be multiplied together? If so, how do we do it? Let's take a look at a few examples and see if we can answer some of these questions. Let's get to it. And this will be our first example. Here we have a couple of matrices A and B in their natural habitat. Aren't they lovely?
Yes, very nice. Aren't they beautiful?
We're going to try and find the product of matrix A times matrix B, and then later on matrix B times matrix A, and just see what happens. Let's look at the first one, matrix A times matrix B. Let's just write it out. There we go. Matrix A times matrix B, and nothing between them to signify that we are finding the product. So you may be thinking, the orders are different of these two matrices. Can they be multiplied? The answer, yes. For addition and subtraction of matrices, the orders of the two must be the same. But for matrix multiplication, the orders may be different. And in fact, they have to be a certain order relative to each other for multiplication to work. So let's give it a try. I'm not sure what order the final matrix is going to be, but hopefully this is big enough. To multiply matrices, we take the numbers in the rows of the first matrix, multiply them correspondingly to the numbers in the columns of the second matrix, and add the results together. That's a mouthful.
And that has to be done for each element that goes into the final matrix. Wow, that does indeed sound very difficult. But when you see it done, it's not as tricky as you'd think.
Alright, demonstration, here we go.
To get the first entry for the answer matrix, let's highlight the first row of the first matrix and the first column of the second matrix.
3 times 7 gives 21. 5 times negative 8 gives negative 40. And finally, 1 times 0 gives 0. That gives us a result of negative 19, which goes down here. So maybe here you can notice that the number of rows in the first matrix is going to be the number of rows in the final answer, like that. And the number of columns in the second matrix is going to match the number of columns in the final answer, like that. A little bit more on that later. Let's try the next entry to get this one. Let's do it. 3 times negative 2 is negative 6. 5 times 3 is 15. And 1 times 1 gives us 1. This gives us a result of 10. For our third entry, we're going to go back and look at the second row of the first matrix and the first column of the second matrix. Once again, here we go. 6 times 7. 0 times negative 8. Negative 4 times 0. Giving us 42. And with a little practice, and once your confidence builds up, hopefully you can do these in your head in one go. Let's try it. 6 times negative 2 is negative 12. 0 times 3 is 0, still leaving negative 12. And finally, minus 4 times 1 giving negative 4. So negative 12 minus 4 gives negative 16 for our final element. Looking good. Let's try the next one. So the matrix B times the matrix A, we've got it written out. Let's give this a try. What will be the order of the matrix B times A? I wonder.
You haven't really explained that clearly enough yet. How are they supposed to know? Do your job.
Well, I'm just giving them a little time to think about it.
Fair enough. Good idea.
What do you think the order of matrix B times A will be, eh? As we said over here, the number of rows of the final matrix will be the same as the number of rows of the first matrix. So we will have 3 rows in the answer. And the number of columns in the second matrix tells us how many columns will be in the final matrix. So we're going to have 3 columns in the final matrix. Weird. This one is a 2 by 2 matrix. This one's going to be a 3 by 3 matrix. Different.
Aren't matrices mysterious? If you multiply the same 2 matrices in different orders, you get completely different answers. Do-do-do-do-do-do-do.
We might come back to that later. Let's try this process here. 7 times 3 gives 21. Negative 2 times 6 gives negative 12. 21 minus 12 is 9. Next, 7 times 5 is 35, plus negative 2 times 0 is 0, leaving 35. And for the last element in the top row, 7 times 1 is 7. Negative 2 times negative 4 is 8. 7 and 8, 15. Let's keep going. Second row to first column. Negative 8 times 3 is negative 24. 3 times 6 is 18. Negative 24 plus 18, negative 6. Second row, second column. Negative 8 times 5 gives negative 40. 3 times 0 is 0, negative 40. Second row, third column. Negative 8 times 1, negative 8. 3 times negative 4, negative 12. Negative 8 minus 12, negative 20. Third row, first column. 0 times 3 is 0. 1 times 6 is 6. Third row, second column. 0 times 5 is 0. 1 times 0 is 0. 0. And finally, third row, third column.
Come on everyone, what will be the final entry? Can you beat him to it? Remember, you should have a pencil and paper in front of you and be trying to get the answer before he does. The more you do that, the greater the mathematician you will soon become. Don't just be sitting there waiting for the answer to be given to you now.
Negative 4.
Did you get it?
So there we have it, matrix A times B and matrix B times A. But what about the sizes, or in other words, the order of the two matrices? Let's just take a little look at that and see if we can figure out what's going on. In the first one, the first matrix has order 2 by 3. And the second matrix has order 3 by 2. The number of columns in the first matrix, in this case 3, must be the same as the number of rows in the second matrix, which is also 3. So when set out like this, these two inside numbers, when we write the two orders, must be the same for matrix multiplication to be possible. And you'll notice that the order of the result is a 2 by 2 matrix. So these two outside numbers, when the two orders are written like this, actually tell us the order of the final matrix, in this case 2 by 2. And in our second example, we can see the same thing happening. Two inside numbers in the order are both 2's. They match up, so matrix multiplication is possible in this case. And the two outside numbers are 3 and 3, telling us the order of the final matrix will be 3 by 3. It is just a coincidence that these are both square matrices. That does not always have to be the case. On to example 2. Let's get a little bit more practice. We have the matrices P, Q, and R. Let's try and find these following matrix products. The first one, matrix P times matrix Q. There they are written out. But is the matrix P times the matrix Q able to be done? Looking at the orders, we have 3 by 2, 2 by 3. The two inside numbers match up and they are both 2's, so yes, this product is possible. And it is going to give us a 3 by 3 matrix as our answer. Let's do it. 5 times 1 gives 5. Negative 1 times 2 gives negative 2. 5 minus 2 is 3. 5 times 6, 30. Negative 1 times negative 3 is 3, 33. 5 times 5, 25. Negative 1 times 0, 0. Leaving us with 25. Second row. 3 times 1 is 3. 6 times 2 is 12. 3 plus 12, 15. 3 times 6, 18. 6 times negative 3, negative 18. Yielding 0. 3 times 5, 15. 6 times 0, 0. Leaving 15. 2 times 1 is 2. Negative 2 times 2 is negative 4. 2 minus 4, negative 2. 2 times 6, 12. Negative 2 times negative 3, positive 6. 12 plus 6, 18. 2 times 5 is 10. Negative 2 times 0, 0. 10. And there is our answer, a 3 by 3 square matrix. The next one, let's multiply matrix P and matrix R. Written out, there they are. So what will be the order of our resulting matrix? Looking at the orders, we have a 2 and a 1 on the inside. They do not match up. So unfortunately, this matrix multiplication is not possible. So in this case, we would simply say that the product is undefined, or simply just not possible. C, moving on down to matrix Q times matrix P. Written out, there they are. Let's take a look at the orders of Q and P. So we have a 2 by 3 and a 3 by 2 matrix. The numbers inside are both 3's, they match up, so this matrix multiplication is possible, and it will give us a 2 by 2 matrix, given by these two outside numbers here, brought down to give us a 2 by 2 order. Let's do it. 1 times 5 is 5. 6 times 3 is 18, giving 23. 5 times 2 is 10. 23 plus 10, 33. Next one. 1 times negative 1, negative 1. 6 times 6, 36, giving 35. And 5 times negative 2 is negative 10. 35 minus 10, 25. Next one is 2 times 5 is 10. Negative 3 times 3, negative 9. 10 minus 9 leaves 1. 0 times 2 is 0, still leaving us 1. And our final entry. 2 times negative 1, negative 2. Negative 3 times negative 6, negative 18, leaving negative 20. And then finally 0 times negative 2, 0, leaving us with that negative 20. So once again, here we have it. Matrix P times Q and matrix Q times P, giving two completely different matrices with different entries and different orders. Just a quick word on that. So when looking at the products of normal, regular, real numbers, we can actually multiply them in any order and get the same result. 5 times 3 is 15. 3 times 5 is 15. No problem. And we call this the commutative property of real number multiplication.
But with two matrices, A and B for instance, if we are looking at
Matrix A times matrix B and matrix B times matrix A,
then the two resulting matrices are, most of the time, completely different.
the matrices have a different order or size, and the entries are different as well. So with matrices, multiplication is not commutative. Sometimes by coincidence it might work, but generally matrix multiplication is not commutative. Multiplying matrices in different orders will give different results. And our last one, matrix R times matrix P. Written out, there we go. Maybe this is not possible. Remember what happened with this matrix R up here.
Maybe. Can't we do a little better than maybe?
Alright, I'll check just in case it can be done. Sheesh. Looking at the orders, there we go. See, I told you, we can't do it. We've got a 3 and a... Oh, they're both 3s. It can be done. Alright, okay, I didn't notice.
Do you seriously consider yourself a teacher?
You're right, I'm wrong.
Absolutely useless.
So looking at these, the result of our multiplication is going to give a 1 by 2 matrix, like this. It's actually going to be a row matrix, isn't it? Let's do it. 4 times 5.
Again, everyone, here's another chance to work out the answer before he does. While you're doing that, I'll see about getting a replacement teacher to get rid of him. Hello, recruiting? Yes?
Continuing. 4 times negative 1, negative 4. 0 times 6, 0. Negative 9 times negative 2 is positive 18, minus the 4 gives us 14. There we have it, matrix multiplication. Remember, the orders of the two matrices you're multiplying must be special compared to each other in that way that we explained, and matrix multiplication is not always possible. I hope you're ready for a little bit more practice because it is now your turn again. Want to try example 3? Given the matrices X, Y, and Z, find the following products. In C and D, does the matrix Y times Z equal the matrix Z times Y? Probably not, right? Are any of these products not possible? If so, which one? Did any of these give a final matrix which was a square matrix? And with these, something very interesting happens. What interesting thing is it? Please feel free to share your answers in the comments. And as always, thank you for watching.